Imagine pulling out your phone to check the weather. You can see that a rainstorm is going to hit your exact neighborhood at 3:15 p.m. Now imagine opening an app to see if a massive earthquake will hit your city at 5 p.m. You can't do it. Every year, the Earth produces millions of tremors. Most are so tiny you could sleep right through them. But occasionally, one strikes with enough force to level city blocks and collapse highways in a matter of seconds. We have satellites scanning the globe and computers processing billions of calculations per second. Why does pinpointing the exact time and place of an earthquake remain scientifically impossible? It comes down to where the action happens. The atmosphere above us is fluid and transparent, letting meteorologists track weather fronts as they form. The Earth's crust is solid rock, completely hidden from view, and incredibly chaotic. The outer shell of our planet is actually a collection of massive fragmented plates. These slabs of rock are constantly grinding against one another at a very slow pace. When the edges of these plates get caught and locked together, immense physical stress begins to build up. The movement doesn't stop. Instead, this tension accumulates deep inside the rock for decades or even centuries. Eventually, the rock reaches its limit. It can no longer hold that built-up tension, and it breaks. That sudden break releases stored energy as seismic waves, shaking the ground above. We know that locked rock will eventually break. We can see the accumulated strain, but calculating the exact millisecond those geological structures will give out is impossible. The Earth's crust works the exact same way. Because of that unpredictability, geologists draw a firm line between two concepts. Forecasting is calculating the probability that a quake will happen in a broad region over years. Prediction is giving an exact time, location, and severity. We are actually quite good at forecasting. We use high-precision GPS networks and satellite radar to measure how the ground is warping by mere millimeters. This tells us exactly where the Earth is being squeezed. Scientists are even feeding millions of historical Earth movements into artificial intelligence programs, looking for microscopic patterns in the data that human eyes might miss. This digital display shows how scientists map complex seismic activity as it happens. When a rupture does occur, they track the overlapping data arrays in real time to pinpoint the exact depth and mechanism of the quake. But knowing that a region is under intense pressure and recording a quake as it starts is very different from identifying the final grain of rock that will fail. Finding that exact trigger point remains out of reach. The first problem is depth. Earthquakes begin miles underground, far below the reach of any camera or sensor. We cannot observe the physical condition of the locked rock directly. Every fault line acts differently. Some slide past each other smoothly, releasing energy in tiny increments. Others lock up tightly for millennia, hoarding energy. Because these cracks lack uniform rules, we can't map past earthquakes on a calendar to predict the next snap. Then there is the issue of false signals. People point to odd animal behavior or strange gas emissions as warning signs. The reality is that these events happen frequently without earthquakes, and many massive quakes strike with zero preceding signs at all. The subterranean environment is deeply chaotic. A microscopic, undetectable shift in fluid or rock pressure miles below our feet can set off a massive chain reaction. The conditions are too complex for an exact timeline. We cannot tell you a quake is coming tomorrow, but modern technology can detect a quake the very millisecond the underground rupture begins. An earthquake releases two types of energy. First is a fast-moving P wave, causing little damage. Behind it is the slower, destructive S wave. Surface sensors pick up the fast P waves immediately, instantly calculating the rupture's strength before heavy shaking reaches the surface. This triggers an early warning system. A loud, flashing alert is instantly beamed to cell phones miles away from the point where the ground first broke. This system buys citizens anywhere from 10 to 60 crucial seconds of warning before the destructive shaking arrives. That brief window is all you need to take immediate physical action. When the alert sounds, you drop to the floor, cover your head and neck under sturdy furniture, and hold on to protect yourself. Automated systems use those same fleeting seconds to hit the brakes on commuter trains and automatically shut off municipal gas valves, stopping fires before they can start. Because the warning window is short, Proactive preparation in your home is mandatory. Secure heavy bookshelves to walls, locate your gas shutoff, and keep an emergency kit ready. Science may never be able to tell us the exact day the rock will finally snap, but by simply combining early warning technology with household readiness, we don't need a perfect prediction to survive the break.